In this video, we're going to introduce the Fundamental Theorem of Calculus. In many ways, this is the capstone of a first course on calculus. It brings it all together. So the first thing we need to talk about is we need a function that's continuous. So f is going to be continuous, at least on some interval, a, b. All the results we have so far are for continuous functions, so it makes sense to talk about what happens when your function is continuous. Then here we go. This is what the Fundamental Theorem says. It says that the definite integral from a to b of f of x dx, that definite integral comes out to just equal, well, you know what it equals. It is the area under f of x from x equals a to b. And how do you find that area? You do some long, complicated Riemann sum. The limit as n goes to infinity of 1 over of b minus a over n times the sum of f of a plus b minus a over n times I, where I goes from 1 to n. You calculate that all, and it's a mess, right? And sometimes you have a shortcut, and you can just find this by doing some geometry, and you draw some picture, and you break it into shapes. It's like, oh, it's a triangle, it's a semicircle. And you can solve it that way, but it's still messy. Here we go. How do we solve this? It's just big F of b minus big F of a. What is big F? Big F is just an antiderivative. It's an antiderivative of little f. So the derivative of big F is little f. So that's it. You want to solve a definite integral? Don't worry about Riemann sums. Don't worry about geometry. Just find the antiderivative and plug in the limits. Plug in the a, plug in the b, and you're done. That's it. Like, let me just show you some examples. This makes everything so much nicer. Here's one. What's the area from 0 to 1 under x squared? Under x squared dx. Okay, so you could draw this out if you want to, right? You could draw your little parabola. You'd be like, oh, that's my little parabola. And you can try and think about what is this area from 0 to 1? What is the area under that parabola? It's not a geometric shape. That's not a triangle, right? It's curved. It's not a triangle. It doesn't have a nice geometry to it. You could do the Riemann sum. We've done problems like this before. It's a mess. But now, with the fundamental theorem, all you have to do is, well, think, what is the antiderivative? So here my function, little f, is x squared. My function inside is x squared. So what is the antiderivative? What is an antiderivative of x squared? Well, the antiderivative is 1/3 x cubed. Remember, it's the power rule in reverse to get the antiderivative. 2 goes up to 3, but then, so when the derivative goes this way, you want the 3 to cancel the 1/3. So you need the 1/3 up front, 1 over the power you increase it to. Now, typically, you would put a plus c to indicate there could be any constant you want. But since we're going to be plugging in 0 and 1 and subtracting this, and since we're going to be doing 1/3 of plug in 1 cubed minus plug in 0 cubed minus 1/3 of 0 cubed, you don't even need that plus c, because what would that plus c be? Well, you'd have plus c, but then you'd be minusing the plus c again, because it's plug in the 1, plug in the 0. Here I'm just doing f of the top, 1, minus f of the bottom, 0. And so if I put this plus c, they're just going to cancel. That plus c minus that plus c will just cancel each other. Whatever, if the constant was 2, it would be plus 2, then minus a copy of 2. It would cancel. So you don't even need the plus c. Simpler than even before. You don't even need the plus c. You just need the 1/3 x cubed. You plug it in. 1/3 of 1 cubed minus 1/3 of 0 cubed. That's 0, so just 1/3 of 1, so just 1/3. That's it. The area is 1/3. That area right there is 1/3. And we found that just by finding the antiderivative and then plugging in the ends. Plug in 1 minus plug in 0. Like this changes everything, right? Let's do another example of this. So let's do an example with let's say cosine. So you know what the cosine graph looks like, right? What does the cosine graph look like? Let me draw a little graph here. So my cosine graph at 0, cosine is 1. So I think my cosine graph looks something kind of like this. and then it continues. But I want to just think about this cosine graph from, say, I don't know, negative pi over 2 to pi over 2. Because those are the two places where cosine is 0, right? Yep, that's where it's 0. Up here it's 1. So here's my graph of y equals cosine of x. And I want to figure out what is this area? What's the area of one little hump of cosine? How much area do you have there? So that's asking me to figure out what is the definite integral from negative pi over 2 to pi over 2 under cosine of x dx. And you might be like, oh, is that a semicircle? No, it's not actually a semicircle. A semicircle is a little bit, it doesn't quite look like this. This height is 1, this over here is not 1, right? So this distance is not 1, it's pi over 2. So it's not a semicircle. You can't use geometry. You can't use a Riemann sum. Those methods would fail, but the fundamental theorem lets us solve it. How? Well, we say, well, here's my function. My function is cosine of x. So what is my antiderivative? The derivative of what is cosine? The derivative of sine is cosine. And typically you would put a plus c, but for these you don't even have to worry about the plus c because they're going to cancel anyway. So don't even worry about the plus c. It's just an antiderivative is just sine. You don't need a constant at the end. And now what you're going to do is you're going to do your antiderivative with one bound, pi over 2 plugged in, minus the antiderivative of the lower bound of minus pi over 2. And so that's just sine of pi over 2 minus sine of minus pi over 2. Okay, so you kind of like think about unicircle. Pi over 2, I'm up at 1. I'm up at height 1 here, minus a negative pi over 2. I'm at negative 1 minus negative 1. Well, there you have it. 1 minus negative 1, 2. This area is 2. Like, that's kind of incredible. Like this whole area is 2, which means half of this area, it's nice and symmetric. We'll talk about this more in a later video. But this is nice and symmetric. So this half here is area 1, and this half here is area 1. Like it's really quite beautiful. The area under the cosine graph is just 1 here and 1 here. This whole hump has area 2 under it. That's it. That's how the fundamental theorem works. You just plug in your values for b and a into your antiderivative, and you just see what you come out and get. And that's all you have to do. That's how you calculate definite integrals using the fundamental theorem of calculus.